Hey everyone, today we're pulling back the curtain on this incredible, invisible force that powers, well, pretty much everything, from a roaring campfire all the way to the phone in your hand. We're talking about the world of hidden chemical energy.
I mean, it sounds like a riddle, doesn't it? One is just wild, hot, totally chaotic. The other? It's cool, controlled, super compact. But believe it or not, they share this deep, fundamental secret. Stick around, and we're going to figure it out.
And boom, there's our answer. Both of them, the bonfire and the battery, are absolute pros at unlocking chemical energy. You can picture it like a coiled spring, just wound up super tight inside the bonds holding atoms together. It's just pure potential, you know? It's sitting there, waiting for the right trigger to spring loose and actually do some work for us.
And look, this energy isn't some weird, abstract thing from a textbook. It actually exists in two main states that you and I see and interact with, like, every single day. So let's break them down.
So on one hand, you've got potential energy. That's the stored up power, right? It's the gasoline in your car before you turn the key, or the wood in a log before you light it up. Then on the other hand, you have kinetic energy. That's the energy of motion. It's the car actually moving, or in our example, it's the heat and light just pouring off of a fire. Really, the whole game, the entire secret, is just converting that before potential energy into the after kinetic energy.
And you know, humanity's first and probably most dramatic way of pulling off this conversion, yeah, it was just setting things on fire.
Okay, so the fancy scientific name for this is combustion. It's what's called an exothermic reaction. But don't let the word scare you, it's just a cool way of saying it releases energy outward, usually as heat. The stuff getting burned, that's the fuel. And it reacts with something called an oxidizer, which for us here on Earth is almost always the oxygen just hanging out in the air.
So how do we actually measure all this heat? Well, this isn't just guesswork, you know. When a reaction spits out heat, scientists can actually measure it with some amazing precision. But that begs the question, right? How in the world do you capture something as slippery and fleeting as heat?
Well, you use a device called a calorimeter. And get this, you can actually make a simple version with a coffee cup. Seriously, the idea is just beautiful in its simplicity. You kick off a chemical reaction inside the cup of water. All the heat from that reaction gets soaked up by the water. And by measuring exactly how much the water's temperature changes, you can figure out precisely how much heat the reaction kicked out.
And this is the recipe they use to figure it all out. Now, I know, the equation looks a little intimidating, but it's really just a simple formula. It lets you plug in the mass of the water, this thing called its specific heat capacity, that's the CP part, and that temperature change you just measured, and boom, the result, Q, is the total amount of heat. The really crucial thing to get here is that we can put a real, hard number on that energy. But let's be honest, burning things is, well, it's messy, it's chaotic. It's like a dam breaking all at once, just this huge, uncontrolled flood of energy. So what if? What if we wanted that same power, but we wanted it released in a controlled, orderly way? Kind of like channeling all that water through a turbine instead of just letting it flood everything. Well, that right there, that's the huge difference between heat and electricity.
And that brings us to path number 2, a much more elegant way of releasing chemical energy, actually taming the flow of the electrons themselves.
So, the device that pulls this off is called a voltaic cell. You might also hear it called a galvanic cell. But you know it by a much simpler name, a battery. That's all it is. It's basically a little engine designed to make electricity straight from a chemical reaction that just wants to happen spontaneously.
Okay, so chemists have this cool shorthand for describing a battery, kind of like its chemical blueprint. I know it looks a little weird at first glance, but it's really just a simple map. It tells us we've got two different metals. Here, it's zinc and copper, and they're separated by something called a salt ridge. The entire setup, the whole point, is to make electrons flow from one side to the other down a nice, orderly path. That is the key. It's a controlled, predictable journey for that energy. All right, so we've got our chaotic bonfire on one side and our controlled little battery on the other. They seem like total polar opposites, right? But now we get to the big reveal, the one single chemical principle that ties them both together.
It all boils down to something called a redox reaction. Now, that's just short for oxidation reduction. And all it really means is that in these reactions, electrons are literally jumping from one atom to another. That transfer, that movement of electrons, that's the secret sauce. That's everything. In a fire, it's a total chaotic mess of electrons jumping all over the place. but in a battery, it's a nice, orderly march of electrons flowing down a wire.
So, how do chemists keep all this straight? Like, which atoms are losing electrons and which ones are gaining them? Well, they use this fantastic little mnemonic, and it's super easy to remember. OIL rig. The oil part is easy. Oxidation is loss. So if we go back to our battery example, the zinc atom starts out neutral, but then it gives away 2 negatively charged electrons. And when it loses that negativity, its own charge becomes more positive. Simple as that. We say it has been oxidized. And the rig part, you probably guessed it, reduction is gain. The copper ion, which started out with a positive charge, swoops in and grabs those 2 electrons that zinc just gave up. By gaining that negativity, its charge gets reduced back down to neutral. So you see, one atom loses, another one gains. That's the entire transaction right there.
And this is where it gets really cool, because once you understand that you can actually control this flow of electrons, well, you can do some truly incredible things. You're not just getting raw energy anymore. You're using electricity like a precision tool. A great example is electroplating. What we're doing here is basically running a battery backwards. We use an outside power source to force those electrons to move where we want them to, and in the process, we can deposit a super thin, absolutely perfect layer of one metal right on top of another.
And this isn't just for making things look pretty, although it does that too. We use it for all sorts of super practical reasons. Think about it. Protecting car parts from getting all rusty, making jewelry shine, improving the electrical connections inside your phone, even reducing friction on giant pieces of machinery. It's an unbelievably powerful and precise technique.
The guy who really cracked this whole code was the absolute genius, Michael Faraday. He was the one who realized there's a direct, predictable, mathematical relationship going on here. The amount of electricity you pump in is directly proportional to the amount of chemical stuff you can move around. It's not magic, it's just math.
And this number right here, this is the key to the whole thing. It's called Faraday's constant, and you could kind of think of it as the secret conversion factor for all of electrochemistry. It tells you that if you have what's called a mole of electrons, which is really just a chemist's way of saying a specific, absolutely enormous number of them, they will carry exactly 96,480 coulombs of charge. This number is the magic bridge between the physical stuff you can actually hold and weigh and the invisible electricity it can generate.
So think about the journey we've just taken. We went from the wild, chaotic energy of fire all the way down to the precise, controlled movement of individual electrons. We've learned that we can measure this energy, we can predict it, and we can harness it. And all of that leads to one final big question. If our understanding is this precise today, what in the world will the batteries of tomorrow even look like?